In this video, we'll discuss compound interest. Now, compound interest is actually more common than simple interest. And what happens with compound interest is that we take the interest that we gain from one time period, we add it to the principal, and that becomes the new amount that gets interest on it in the next time period. So if we think about $100 having a 10% compound interest monthly, that would mean if we started with $100, after the first month we gained 10%, but now we have $110 in the account. So when we go to month 2, we're no longer basing the principal off of where we started, but we're basing it off of where we ended month 1. So now our new principal is actually $110, and we're taking 10% of $110 instead. So now that creates a new amount of $121. When we go to the third month, we're no longer using the $100 or the $110. We're going to use that $121 to calculate our new interest. And so we take 10% of the $121 and see that we'd have $133.10. Now look what's happening to the amount of interest we gain from one month to the next. We go from $10 to $11 to $12.10. Because our principal increases, the amount of interest we gain increases with each time. And when we look at the amount in our account, over time, especially a long period of time, there will be an exponential growth in that account. That's one of the reasons why you are supposed to invest in your retirement at an early age. Because if we can start with a small amount, the interest we can gain over time will slowly move at an exponential rate that will gain even more as we're about to retire. So the formula we use for compound interest is A equals P times the quantity 1 plus R divided by N raised to the N times T. It's a lot of letters, but let's just talk about them. The first one, A, is our future value. That's how much will be in the account after we've done this compound interest. P is still our principal, the original amount we invested in the account. R is our interest rate, which will often be called the nominal interest rate, and that's written as a decimal, not as a percent. So we always have to remember to take our percent, divide by 100. T is our time. It's the number of periods in which interest will be paid still. Often it's an annual interest. And then that N is our new letter we haven't seen before, and that's telling us how many times are we computing the interest in a single year. Now we have some very common ones that we often will do, which are monthly, which means that you're compounding the interest 12 times in a year. Quarterly would be 4 times. And then if you see something bi or semi, that's going to be, you've got to think about what does that mean. Biannual will be 2 times. Bi-monthly could mean, bi-monthly often will mean 6 times. You do it every 2 months, whereas semi-monthly may mean 24 times because you're doing it twice each month. So pay a little bit of attention to those words, but primarily you're going to see monthly and quarterly in most of your problems. Now, let's look at some examples to help us understand how to calculate with compound interest. So Sierra invests $3,000 in an account that pays an annual interest rate of 4% compounded quarterly. How much money will Sierra have in the account after 3 years? So first thing, our future value. That's what we want to find out. The principal, well, Sierra invested $3,000. The interest rate we have is 4%, and that's so 400ths. Remember, we got to write as the decimal. Our time, we're told this is an annual interest, and we're doing it over 3 years, so that's our T will be 3. And the new thing is our compounding, and we're compounding quarterly, and quarterly means 4 times for that N value. We have every value accounted for, so now we can substitute into our equation and find what our future value for Sierra will be. So this will be 3,000 times the quantity 1 plus 400ths divided by 4 raised to the 4 times 3. We're going to follow our order of operations. I'm going to do 2 steps here at the very beginning. I'm going to divide my 400ths by 4, and I'm going to multiply my 4 times 3 in the exponent because they're individual and it won't affect how we solve this problem. It'll all get done. If you need to separate those steps, by all means, go ahead and separate them. Now I follow my order of operations, which says deal with my parentheses first. Now I have a value raised to an exponent. that gets done before multiplication. So there's my exponent, that's done first. Now I can multiply, and I will end with $3,629.49. That means that Sierra will have $3,629.49 in her account after 3 years. So in essence, in 3 years, she gained about $630 in this account. Let's look at another example. Say that Aaron deposited $875 in an account 5 years ago that earned 7.8% annual interest compounded biannually. How much money does Aaron currently have in the account? So we're trying to determine this amount in the account that we call it technically the future value, but in this case, it's that current value. It's what we don't know because everything's based on the past. Now we do know how much was originally put in the account, which was $875. We also know that the interest rate was 7.8%. That's our nominal interest rate, and 78 thousandths. We know that from time that it's an annual interest, and it started 5 years ago. So our time that we're looking at really is 5 years. And last thing is the compounding. It's done biannually, and we talked about that earlier, meaning 2 times in a year. If it was semi-annually or biannually, we know that means 2 times in a year. So now we can substitute in all these values into our formula. We don't know the future value or how much Aaron has, but we do know the principal, we know the interest rate, we know the compounding, and we know the time. So like the former problem, I'm going to divide inside the parentheses, and I'm going to go in and simplify my exponent as well. Now I can add within parentheses, and then I raise my parentheses to the exponent because I'm following order of operations. Now I can multiply by the $875, and this will give me $1,282 and then 811 thousandths. Now I did it to the 3 decimal places because when we're dealing with money, we always round to the nearest cent, which is the 2nd decimal place. So if I look to the right, the thousandth is 1, so I'm going to keep where I am and say that Aaron currently has $1,282.81 in his account. Now, you heard me say a couple times the word nominal interest rate, and that's because really in a compound situation, we have both a nominal interest rate and an effective interest rate. The nominal interest rate is the interest rate that we have before any of that compounding occurs. That's that R value. Whereas the effective interest rate is the interest rate at which the principal actually increases in a single year with that compounding effect. So if we want to calculate the effective interest rate, what we do is we're going to take and do the quantity 1 plus R divided by N raised to the N, and then subtract 1. And this is because this will give us that decimal place to say about the compounding, but if you don't have it greater than 1, it actually will shrink based on how exponents work. That's why we have to do the 1 plus and then subtract the 1 at the end. So let's look at an example where a savings bond provides a 3% annual interest rate that compounds every 2 months. What's the nominal and effective interest rate of the savings bond? So we'll start with the nominal interest rate. That's provided as the 3%. Now we can say, okay, let's figure out the effective. We need to know the compounding. And they tell us it's done every 2 months. So the 2 is not what we need. We need to say that since it's happening every 2 months, that's 6 times in 1 year. So now I can substitute in what I have. I have my nominal interest rate written as a decimal, and then I have my compounding of 6 for the ends. I divide my 300ths by 6, then I'm going to add 1, and then raise that to the 6th power. And again, if I didn't have the adding 1, my 500ths would get, or my 5,000ths would get much, much smaller instead of showing exactly what's happening. So it is, in essence, a requirement to make this work. And that will give me 1 and 304 10,000ths. So I subtract the 1, and here is my effective interest rate. But remember, this is written as a decimal, and we talk about interest rates as percents. So multiply this by 100, and you'll see that effectively it's given us 3 400% in a year. Now, you look and say, well, that's not that much different. But think about if you start investing very large sums of money. That 0.04% can change how much money you make in a year by hundreds or thousands or even millions of dollars, depending on how much you started with in the first place. Let's look at another example to help make this point. Say that a savings bond instead does 5.7% annual interest rate that compounds monthly. We want to know what's the nominal and effective interest rate in this case. So we know the nominal is what's provided, the 5.7%, and it's telling us that we're compounding monthly. That means 12 times in the year. So we're going to use our effective interest rate and say that that's 57 thousandths divided by 12. And we're then going to add 1 and raise it to the 12th power. And when we do that, we end up with 1 and 585 ten-thousandths minus the 1, and that gives us that interest rate. And we got to remember again that 585 thousandths, that's the decimal we needed as the interest rate. So we multiply by 100 and see that would be 5 and 85 hundredths percent. So by compounding, we're getting an extra 15 hundredths of a percent each year. And think about how that will affect the principal in an account over many years. This can have a huge impact, which is why compound interest is so important to understand.